Hello guys, welcome back to my channel. I know it's been a while since I last uploaded, but I'm finally back. And in today's video, I'll be going through IGCSE Physics paper 4 for the October-November series, and I'll be going through paper 43. I've done paper 41 and 42, so if you haven't checked them out, make sure to go to my channel and then check them out. So today I'll be going through the paper and going through each question and explain them on how to do each and every question. So let's start with the number 1. A. Oil of density 0.8 gram per centimeter cubed is poured gently onto the surface of water of density 1 gram per centimeter cubed. The oil and water do not mix. Describe and explain the final position of the oil relative to the water. So oil has less density than water, as they've told us. So in the description, the oil would float. It would float on the water. And explanation is because oil has less density than water, or lower density than water. Part B. An irregularly shaped object has density of 2.7 gram per centimeter cubed. Describe a method to measure the volume of the irregularly shaped solid object. So to find the volume, what we can do is, let's say we can have like a measuring cylinder. Let me just redraw that. So we have a measuring cylinder with their readings, of course, and then we fill it up with water until a certain reading, and then we put the irregularly shaped object into the water. Then what we see is we see the level rise. Let's say if it rises to this point after the object has been added, then we can subtract this value from this value to find the volume. So in writing, we can say measure an initial volume of water, and then after that we immerse the object, and then we measure the final volume, and measure final volume, and then we have to calculate the change in volume, and then calculate change in volume. That would be our answer. Part 2. The volume of the object is 83 centimeters cubed. Calculate the mass. So we know that we have a density of 2.7 grams. So we know that density is mass over volume. So to find mass, we can rearrange to make it mass equals density times volume. So the mass would be 22.7 times the volume, which is 83. So that should give us 224.1. We can round it to 224 grams, of course. Let's move on to question 2. Figure 2.1 is a graph that shows how the extension of a spring varies with the load suspended from it. Determine the spring constant of the spring. So the spring constant. So to find that, first we have to use Hooke's law. So it says that the force is equals to the spring constant times the extension. So over here we have the formula, and the extension is 4 centimeters when the force is 40 newtons. So what we can do is we can replace the values. When the load is 40 newton, it would be K times 4. So we can divide both sides by 4. So the spring constants would be 14 divided by 4, which would give us 3.5. And since we divided the force by the mass, it's going to be Newton per meter, or Newton per centimeter in this case, because the extension is given in centimeters. Part 2. On the graph, mark the limit of proportionality and label this point L. So the limit of proportionality is a limit where the spring doesn't obey Hooke's law anymore. So when on the graph, we can mark that point where it starts bending. So somewhere around here maybe, and label it L. Part B. Figure 2.2 shows a car traveling at a constant speed around corner A on the road. Okay, part 1. On figure 2.2, mark with an arrow the direction of resultant force acting on the car as it travels around corner A. So on the diagram we can see that the car is moving in a somewhat circular manner. It's turning. So whenever this happens, the resultant force is always going to be to the inside or to the center of the circle shape. So if this is, let's say, the circle shape, the resultant force would be to the center, this side. So we can remove the other stuff so it would be easier to see. So that would be the arrow. It would be slightly to the center. Part 2. Corner B has a smaller radius than corner A. The car travels at the same speed around corner B as around corner A. Show how the resultant force changes due to the car traveling around a corner of smaller radius. So here they're telling us that on the diagram we can see that corner A, the turn is smoother than corner B. So because corner B has a sharp turn and corner A has a smoother turn compared to corner B. So that means, and if the car is traveling at the same speed, so when turning at corner B, they would be higher forced towards the center. So we can say the force increases. Question 3. Figure 3.1 shows a boy throwing a ball at an object in a fairground. The ball has a mass of 190 grams and travels horizontally with a constant speed of 6.9. Calculate the momentum of the ball. So we know that momentum is the same as, is the same as mass times velocity. So the mass is 190 grams, which we have to convert to kilograms. So 190 over 1000 times the speed is 6.9. So when we do that, 190 over 1000 times 6.9, that would give us 1.3 kilograms meter per second. That would be answer. We can just write it down there. Part B. After hitting the object, the ball bounces back along the same straight path with a speed of 1.5. The object has a mass of 1.8 kilograms. Calculate the speed of the object after it is hit by the ball. So what they're telling us in this question is the ball hits the object, and when the ball was hitting the object, the momentum was 1.3, and then the ball, after hitting the object, goes back with a speed of 1.5. Yeah, 1.5. And then this object is going to be 1.8 kilograms. Now we're told to find the speed of this object. So now we use the conservation of momentum. So the momentum before collision is equals to the momentum after collision. So the momentum before collision is 1.3. So 1.3 should be equals to the momentum after collision. So now we have two bodies in the second part. So the first one is a ball, which is moving at 1.5 meters per second. And the momentum is mass times velocity always. So The mass of the object, it's given 190 grams. This is the same as saying 0.19 kilograms. This is the momentum of the ball. And then we have to add it to the momentum of the object. So that's going to be 1.8 times v, the velocity which we have to calculate. But then, in this question, the ball bounces back. So that means the velocity is in the opposite direction. So now we have to use minus 1.5 instead. So we do this minus 1.5. So now we just solve for v. So 1.3 equals minus 1.5 times 0.19. That would give us minus 0.285 plus 1.8 v. So we add 0.285 on both sides. So that would give us 1.585 equals 1.8 v. So we divide both sides by 1.8. That would give us 0.88 meters per second. That is going to be our speed. Don't forget the units. So that's how we get this 3 marks. Part C. The kinetic energy of the ball is 4.5 joules before the collision and 0.2 joules after the collision. Calculate the change in total kinetic energy of the ball and the object during the collision. So the initial energy before the collision, they told us it's 4.5 joules, and then after the collision, 0.2 joules was remaining. So now we have to find the kinetic energy of the ball and the object during the collision. So now kinetic energy is equals to half mv squared. So it's going to be half times the mass of the object, which is 1.8, times the speed of the object, which is 0.88 squared. So the kinetic energy, that would give us 0.697. So that would be the kinetic energy. So now the initial kinetic energy was 4.5. So to find the change in the total kinetic energy, we subtract this one, 0.6797, and also subtract the final remaining one, the remaining kinetic energy, which is 0.2. In that case, that would give us 4.5 minus 0.7 minus 0.2. That would give us 3.6. That's the change in kinetic energy, joules. Question 4. The lowest possible temperature is 0 Kelvin. State the name of the lowest possible temperature. This is called absolute zero. Nitrogen boils at 77 Kelvin. Calculate the boiling point of nitrogen on the Celsius scale. So to convert it, we just add 273. So we do 7. Okay, sorry about that. That was a mistake. 0 degrees Celsius is the same as 273 kelvins. So to convert from Kelvin to degrees Celsius, we just have to subtract 273. So that would give us 77 minus 273, which would give us minus 196 degrees Celsius. The temperature of a fixed mass of gas at constant volume changes from 300 kelvins to 400 kelvins. State and explain in terms of particles the effect on the pressure of the gas. So statement would be that the pressure would be increased. So increases. Why this would happen is we have a constant volume. So let's take a container, and then we have gas particles. And when the temperature is increased, they start moving faster and they collide more often with the walls of the container and also with each other. So that means when they collide more often with the walls, they would exert higher force on the walls, so there would be higher pressure. So now I just have to write that down. So the first one would be the particles will move faster. And then after that, there would be more collisions, more frequent collisions between the particles and also the walls of container. The walls of container. So they would exert higher force on the wall. So that we can say exerting higher force on the walls. Now this is just enough to get us the 4 marks. Part C. A sample of gas at at pressure of 120 kilopascals, the volume of the gas is doubled at constant temperature. Calculate the new pressure of the gas. So to figure this out, we can use the formula P1 V1 equals to P2 V2. So the initial pressure is 120 kilopascals, but times V1. So, and this volume doubles, so it increases by 2. So when we rearrange the formula, our P2 would be P1 V1 divided by V2. So if this doubles, that means then the pressure would be divided by 2. So let's take V2 to be, let's say, 100. So initially it was 100, so it would be 120 divided by 100. But then when it doubles, it would be 120 divided by 200, if that makes sense. So since the pressure is inversely proportional to V2, when V2 doubles, the pressure halves. So we do 120 over 2, which could give us 60 kilopascals. Number 5. Figure 5.1 is a scale diagram of wavefronts of red light approaching a gap in a barrier. On figure 5.1, draw 3 wavefronts after the wave has passed through the gap. So now through this we have to demonstrate the diffraction of a wave. So this distance is the wavelength. So now we draw arcs, and then the wavelengths should be about the same. So this would be the answer, but let's slightly move it so it would be centered. So those are the wavefronts. Figure 5.2 shows the same barrier and gap A. And a gap. A wave of blue light approaches this barrier. On figure 5.2, draw 3 wavefronts of this wave before it reaches the barrier, and 3 wavefronts after the wave has passed through the gap. So on the second figure they've given us a blue light. In the previous one it was red light. So we know that blue light has shorter wavelengths than blue light. I mean, blue light has shorter wavelengths than red light, so that means the wavelength should be lower. So when we draw this, make sure to make the gap between the waves shorter than the one on the above picture. So yeah, this seems fair enough. So now, since this has a lower wavelength, but the gap is the same, so that means they wouldn't bend as much as the red light did. So let me just use a blue one so it would be clear. So they wouldn't bend as much. They would only bend towards the end. So this would be our answer. Question 6. On figure 6.1, sketch the current voltage graph of a filament lamp and explain its shape. So before sketching anything, we should label the graph first. So on the y-axis is going to be the current, which is measured in amps, and on the x-axis is going to be voltage measured in volts. So the shape of a filament lamp is going to be something like this. It's going to be a curve which is with a decreasing gradient. So explanation, this is because as the current increases, the temperature increases. The temperature increases. So when the temperature increases, that means the resistance would also increase, so there would be a decreasing current. So for our second point, we can say that the resistance increases. So there would be a lower increasing current. Lower increasing current. Let's move on to part B. Figure 6.2 shows a circuit. So this looks like there's a lot of components taken. So let's take step by step. Calculate the reading of the voltmeter. So we have our voltmeter right over here. So on the diagram, we can see that the 12 volt is an alternating current, and we have, it's not a, okay, it's a DC current, and then we have the positive and the negative side. And also on the cell, we have, this is the positive side, and the shorter one is the negative side. Since the negative side is connected to the negative side, that means this voltage and this cancel. So what we can do is 12 volts minus 3 volts, which will give us 9 volts. And the voltage is in parallel, so that means the value wouldn't change. It's going to be the same across the circuit. Calculate the current in the 4.2 ohm resistor. So we know that current is going to be V over R. So the voltage is 9 and the R is 4.2. So that would give us 9 over 4.2, giving us 2.14 amps. Part 3. Determine the current in the 2.1 ohm resistor. Now this is a trick question. It's going to be 0, and I'll show you why. So whenever looking at the circuit, we would look at conventional current. So we'd follow the positive charge. So when we follow the direction of the current would be anti-clockwise. So it goes through here, and then we have the semiconductor diode. Now this is for those who don't know, it's a component that would allow current to pass only in one direction. So if it's facing this way, it will allow current to pass through this direction. So if a current is coming this direction, that means there's no current. And in this case, that's why we have current is coming in this direction. So the semiconductor diode will not allow the current to pass. So that's why the current is 0 amps. Part 4. Determine the reading on the ammeter. Okay. So this is the ammeter, and it's connected in series to the batteries. So what we would usually do is, because since we have like two resistors set up in parallel, we would have combined those resistors. But then, as you can see, we know that current doesn't flow through to the next resistor because of the semiconductor diode. So there's no flow of current here. So we'll just consider this one. So that means we have a 4.2 ohm and a 9 volt. So it's going to be the same as this question over here. It's going to be 2.14 amps. Part 5. Calculate the electrical power transferred in that 4.2 ohm resistor. So we know that power is going to be VI. So our V is 9 times the current, which is 2.14. That would give us 19.26, which can be rounded to 19. So our power is going to be 19 watts. Don't ever forget the units, it's very important. Question 7a. Figure 7.1 shows electric field pattern around point X. So this is a diagram. On figure 7.1, draw an arrow to indicate the direction of the force on a negative point charged at point Y. So we have to draw an arrow to indicate direction of the force on a negative point charge placed at point Y. So a negative point charge is placed at Y. So now we have to draw the arrow. So for this question, what we have to understand is what these arrows represent. So in an electric field pattern, the arrows represent the direction of positive charge. Direction of a positive charge. So in this case, all of them are going outwards. And we have a charged particle at X. So if the positive charges are going away from particle X, that makes particle X a positive. So X is a positive charge, or a positive point charge. So if we have a negative point charge, it would obviously be attracted to the positive charge. So we've done part 1. Part 2, state what is at point X to produce electric field shown. So it's going to be a positive point charge. That is the answer. Because if it was a negative, that means for a negative, they would be attracted. The direction would be always towards the charge. But since it's positive, they're being repelled. Part B. A piece of plastic is charged positively by friction. State what charge transfer occurs during this process. So we know that positive charges do not move, it's only electrons or negative charge. So we say electrons. And since the plastic is charged positively, electrons are removed from the plastic. The plastic. Explain how the structure of an electrical conductor differs from the structure of an electrical insulator. So what an electrical conductor has, it has free delocalized electrons. Let me just erase that. Free delocalized electrons. Now these are the charges that would carry the These are the particles that would carry the charge. That's why it's an electrical conductor. So we can move on to the next one. Question 8a. Figure 8.1 shows a single turn coil of a simple direct current. So it's a DC current. That means it would the ring would be only rotating in one direction. Explain the direction of the turning effect as seen by an observer at O. So for this question, to determine the direction of the force, we can use Fleming's left-hand rule. So this is Fleming's left-hand rule. Let me just zoom in. So this shows us we use our left hand and then we have our thumb perpendicular to the index finger and the middle finger. So the middle finger shows the direction of the current. So the current is this side. So the middle finger would be this side, and the direction of the electric magnetic field, it would always be from north to south. So the index finger would be pointing this side. So if we put that way, our thumbs would be pointing upwards. Sorry for the bad drawing, it's really hard to show this. But then our thumbs would be pointing upwards, so it would be pushing this upwards, so it would be rotating like this, clockwise. So we can say force on the left side will cause it to rotate clockwise. That would be what the observer would see. Part 2. The coil is replaced by an otherwise identical new coil with 3 turns and the same current in the coil. So the same current in the coil and with 3 turns instead of 1. Show how the turning effect compares. So if we have a greater turn, that means there's going to be a greater turning effect. So it would be greater. Part 3. A third coil is identical to coil in I, the first part, except its resistance is 3 times greater. So if the resistance is 3 times greater, that means the current decreases. The PD across the coil is the same as the PD in I. Show how the turning effect compares. So if the current increases, that means the turning effect will decrease. Or we can say it's lower, since we're comparing. We can say it's lower. So the rotation is affected by 3 things. The first one is the number of coils. The second one is going to be the current. And the third one is the strength of the magnetic field. So these are the 3 factors that affect the rotation and how fast it rotates. If you're enjoying so far, make sure to like and subscribe for more upcoming content. And since the May June exams are coming up, I'll be making videos about that exam, so make sure to stay tuned for that one. Let's continue with part B. Figure 8.2 is a voltage time graph showing the output of a simple AC current AC generator at times t0, 1, 2, 3. Figure 8.3 is an end view of the plane of the coil of the generator at time t0. The coil is rotating clockwise. Okay, so it's rotating in this direction Draw an end view of position of the plane coil at time t1. So at t1, it's at the maximum. So since it's at the maximum voltage, that means it's going to be horizontal. So the current is maximum at the horizontal position. This is a fact to know. So we have the axis of rotation, and since it's rotating this way, we have A and B over here. Part 2. Draw an end view of the position of the plane of the coil at time 2. Include the labels A and B. At time t2. So at time t2, that means it has returned to its original place. Since t2 is one wavelength away, that means it's a whole rotation. So it would return to its original position. We have A and B. Yeah, that's the original position. Part 3. Draw and view position of the plane of the coil at time t3. So t3, it's also at the maximum. T3 is at the minimum point, so that means it's going to be horizontal, but then it's going to be different because A is going to be on this side and B is going to be on the right side. So since it's largest voltage, it's horizontal. So we have A on this side and B on this side because it has rotated a full 180 degrees. So the answer is going to be a horizontal line, and then we have A and B on this side. Question number 9. A. For each application of radioactive isotopes, state and explain which type of radioactive emission is suitable and suggest an appropriate half-life for the isotope. Okay. We have household smoke alarm. So the type of radiation is going to be an alpha radiation because alpha radiations have high ionization ability. So we can say have high ionization. Because how a smoke alarm works is like if the alpha particles are not penetrating, that means smoke is there, so they will be detected. So alpha particles, they don't have high penetration. So for the half-life of the alpha particles, we can just say 100 years. That is okay. Wait, let me just rewrite that. How did I misspell years? 100 years. So as long as we have something between 1 and 500 years, it's going to be okay. I mean 10 and 500 years, that would be okay. Part 2. Measuring thickness of aluminum strips produced in a factory. So that one is going to be a beta particle. Why? Because beta particles, they have higher penetration than alpha particles, but then lower penetration than gamma particles. So the penetration depends on the thickness. So the penetration depends on the thickness of aluminum. Because if we have used alpha, that means none of it will penetrate the aluminum. And if you have used gamma particles, all of it would be penetrated, so we cannot determine the thickness. And the half-life of particles, it could be any number of years. So we can also say 100 years for this one. The mark scheme for this one says it should be any number of years. Because a beta particle, it's a high-speed electron. Part B. Lead-208 has the highest nuclear number of the stable isotopes of lead. Explain lead-214 is radioactive. So the reason why, in general, why isotopes of atoms are radioactive, it's because one of the reasons it's because they have too many neutrons. So we can say lead 214 has too many neutrons. So it has to decay to remove those neutrons. So it has to decay to reduce the neutrons. Because what happens in a decay is like the the count rate would be decreased by half. So every time it decays, the number of neutrons is reduced. State two different sources of background radiation. So background radiation is the radiation that we always have. So the different sources could be, the first one could be radon gas, which is present in air, so it would always be there. The second one, we can say it's because of food. Third one, cosmic rays. We only need two for this one, but then I'm mentioning the others for your knowledge. And then it can also come from rocks and buildings. These are the sources of background radiation. Number 10, and I believe this is the last question. State what is represented in space physics by HO. So this is Hubble's constant. Write down the equation that defines HO in terms of the speed that a far galaxy is moving away from the Earth and its distance from the Earth. So it's speed and distance. So Hubble's constant is going to be speed over distance. That's the formula for Hubble's constant. And the numerical value of a HO is 2.2 times 10 to the power of minus 18. State the unit of HO. So HO. So we can actually derive it because speed is meters per second and distance is in meters. So the meters cancel, so just remaining with second to the power of minus 1. That's a unit. We can also say 1 over second. This is the unit. Use this value of HO to determine an estimate for the age of the universe in seconds. So Hubble's constant is going to be, where was it given? Yeah, over here. 2.2 times 10 to the power of minus 18, right? And the unit is in seconds, minus to the power of minus 1. So to find the age in seconds, that means we could do 1 over Hubble's constant, which is equals to 1 over 2.2 times 10 to the power of minus 18. That's the age of the universe in seconds. Part B states when cosmic microwave background radiation, CMBR in short, was formed and where we detect it coming from. So cosmic micro CMBR is a microwave radiation which is present all in all of space and all points in space, and then this was formed shortly after the Big Bang theory. So it would be shortly after the Big Bang. And it's detected from all points in space. So that was the last question on space physics. So if you guys want me to make a dedicated video on space physics and how they bring the different types of question and how to tackle each of the question and part of space physics and the revision, make sure to drop it down in the comments and then I'll shortly make it if enough people are interested. But that was the end of the last question. So if you have enjoyed the video, make sure to like and subscribe. So Any comments or suggestions, make sure to drop them down below. And thank you for watching.